Today I am going to talk about amplifier basics. Most analog circuits are some type of an amplifier which takes an input that we call a signal and does something to that and gives us a different output. We usually think of an amplifier as making the input signal larger, but that's not always the case. The general symbol we use for an amplifier is a triangle with an output on the point and an input going to the backside. And this represents most any kind of an amplifier in a generic sense, unless we're getting more specific to what an actual circuit does. There are three basic amplifier configurations. Those configurations are common collector, common emitter, and common base. And they're named because that particular terminal is common to both the input and the output. So let's take a look at some of these circuits. For example, let's look at the common collector. I'll use a bipolar junction transistor, an NPN. And the circuits we're talking about do use bipolar junction transistors, but what we're talking about does also pertain to FETs, and I'll show how that works as we go along. The collector is going to go directly to a power source. It may not always go directly there, but this is the simplified version of the circuit. So we have a power source, which means that somewhere we have a battery going to ground, and we have an input, and our output is on the emitter. And so this is the common collector, and we can tell that's the common collector circuit because the output is on the emitter. So output on the emitter is a common collector. And it's kind of hard to see how the collector is common to both the input and the output. So this is often called an emitter follower also. So let's take away our power source and just look at the circuit proper. So we're going to have some input and some output. Let's say it's a DC input. So let's put an input of 2 volts here, positive. Since it's a NPN transistor, these voltages will all be positive compared to wherever ground is. And the gain of this circuit is going to be essentially the HFE of the transistor. So recall that HFE, uppercase means DC characteristics. And let's say this has an HFE of 10, which means that our collector current will be 10 times our base current. So let's say we have a base current caused by whatever's going on out here to be 1 milliamp. So what is our collector current going to be? Well, HFE says it's going to be 10 times the base current, so our collector current will be 10 milliamps. So our output current is going to be, in this case, 11 milliamps. Why 11? Because Kirchhoff's current law says we have a node here. We have 2 currents going into the node. They combine to one output current. And Kirchhoff's current law says that the output current is going to be the sum of the input currents. And so that's 11 milliamps. So our gain, current gain, is going to be a little more than HFE. But what happens to the voltage? Well, let's reduce some of our clutter around here to see what happens. If we have plus 2 volts here, we're going to lose approximately 7/10 of a volt going from the base to the emitter, positive to negative. So this will end up being positive 1.3 volts on the emitter, because the voltage just simply drops by 0.7 volts. So DC voltage gain is meaningless with a common collector circuit, but we do have a current gain that's a little more than HFE. And we'll talk about that a little bit later, but let's take a look at the AC voltage gain, find out why they say this has a gain of 1. So let's have an input voltage that is a sine wave. Normally it'll be more complicated than that, but just to simplify things, we'll have a sine wave going in. And let's say it goes up to positive 4 volts and down as low as positive 3 volts. So this has to be completely offset above 0, and it has to remain high enough that it never goes below 0.7 volts at the base. Otherwise, this voltage tries to go below 0, and then we're outside the parameters that the circuit can work in. So we have plus 4 down to plus 3. So our peak-to-peak voltage, there's our positive peak, there's our negative peak, if you will, or our trough, but there's a 1 volt difference. So we have 1 volt peak to peak. So what do we have on the output? When this is at positive 4 volts, this is going to be at positive 3.3 volts. 0.7 of a volt difference. When this is at positive 3 volts, this will be at positive 2.3 volts. So we just simply have that offset. So if we have that on the base, our 1 volt peak to peak, let's put that sine wave over here. What comes out is going to be positive 3.3 volts and positive 2.3 volts. There's still a 1 volt difference, so it's 1 volt peak to peak. So the AC voltage gain is 1. Multiply that by 1, we still get the same voltage on the way out. So that's what we have to say about the common collector circuit. If we make it a little more complicated, it becomes a little harder to recognize. So let's go ahead and make it just a little more complex by putting some more resistors in here. Because there could be more resistors in there. Let's give some complete bias to this circuit just to make it as complicated as possible. That's about as far as I'm going to go at this point. So now we have a more complex circuit. How do we know this is a common collector circuit? Because the output is on the emitter. So once again, output on the emitter, common collector. So there's the more complex version of the common emitter circuit. Now, what if this is a field effect transistor? Let's go ahead and draw that in here, because we can make similar circuits with field effect transistors. And so this is the drain, this is the source, and this is the gate. So if we have the output on the emitter of a bipolar junction transistor, here we have the output on the source. So what would we call this particular circuit? We don't call it a common collector because there is no collector, it's a FET, but there's a drain. So the output is on the source. This is a common drain circuit. Now let's go to the next circuit we want to take a look at, and that's going to be the common emitter circuit. So let's start with the same NPN transistor. And of course this could be done with PNP transistors, but the voltages would just be reversed. But let's just keep it simple. Now the common emitter circuit is going to be a little more complex in its simplest form, because we must have a collector resistor here, or the output is just going to be at the voltage. There's our positive VCC there. Well, without this resistor, then this output will just be that same voltage. So we have to have something to isolate that from that voltage there. There are integrated circuits that do not have this resistor, but that just simply means we're expected to put that resistor on ourselves instead of it being in the circuit. We'll talk about that another day when we talk about open collector ICs down the road. So we must have that, and this can be grounded, so let's make it simple. Ground that, and there is our input. So this is the common emitter circuit. How do we recognize that? Well, the output is on the collector. If the output was on the emitter, it was a common collector circuit. But if the output is on the collector, it's a common emitter circuit. And this is the simplest form of that. And this particular configuration is often used as what's called a voltage inverter, because let's take a look at what happens if we have no signal on the input, just 0 volts. Okay, so there's 0 volts. That means there's no current flowing into the base, no current flowing out the emitter. And let's say it has an HFE of 10. As if this matters for what we're going to do for the next moment. There's no current, therefore 0 times 10 is 0, so there's no current flowing into the collector. If there's no current flowing through this resistor, do we have a voltage drop? Remember, to get a voltage drop across a resistor, we need two things. We have resistance and we have to have current. If there's no current, there's no voltage drop, which means the voltage on each side is the same. So now this is equal to the VCC. So let's say that was positive 5 volts there. This is going to be positive 5 volts here. So 0 volts in gives us positive 5 volts out. But now let's put positive 5 volts here. Now we're going to get something greater than 0. We're going to get, depending on what resistor this is and what the HFE is, we'll keep it simple, but we're going to get some current greater than 0 amps. Now we have some current flowing through there. We're going to assume that that is enough current to pull this all the way down to 0 volts. So if this was a 1K resistor here, and we have 5 milliamps flowing through it, well, 5 milliamps through 1K, do your Ohm's law, we find that comes out to be 5 volts. So we start with 5 volts, we lose 5 volts, we're down to 0 volts. We'll see later that we really can't quite get there, but this will do for now. So plus 5 in, we get 0 volts out. 0 volts in, we get plus 5 out. So that's what we call a voltage inverter. That's the simplest thing you can do with the common emitter circuit. So that's a voltage inverter. Let's make it a little more complicated by changing some of these values around a little bit. So let's leave this at 1K. Let's make this 10 volts. And let's say with plus 5 volts here, we have a current of 7.5 milliamps. So 7.5 milliamps across 1K, we're going to lose 7.5 volts. That's going to leave us with 3.5 volts on the collector. Looks like we lost voltage, doesn't it? But let's increase this up to, I'll just draw it above, to plus 6 volts. I want to leave that there just to show us we went up 1 volt. That is going to cause this current to go up to 9.5 milliamps. So that went up by 1 volt, but 9.5 milliamps is going to mean we lose 9.5 volts here. So that means this is going to go down to, let's write it up here, plus 0.5 volts. And so that is going to be a difference of 3 volts. So here we got a change of 1 volt, but here we got a change of 3 volts. And notice that the voltage went down from 3.5 volts to 0.5 volts. Maybe I can put that down here so that we had a change, a drop of 3 volts. So our voltage went up here, and notice that the voltage went down at the collector, but the important thing is we went up by 1 volt and went down by 3 volts. We had what at first looks like a drop in voltage, but we actually have an amplification because the change is 3 times what the change is here. So that's one thing else we can do here, but we don't usually use a common emitter circuit in such a simple configuration because the gain is dependent on the HFE of the transistor, and 2 transistors, even from the same batch, might have different HFEs. And also the HFE changes with temperature. It changes with the collector current. So as we're using the transistor more heavily, the HFE actually changes. So it's not really a very stable circuit. So we usually use the common emitter in a much more complex circuit, sort of what I already showed. Let's just go ahead and show this. Here's our bipolar junction transistor. There's our collector resistor. And we may or may not have an emitter resistor, but let's make it as complicated as we can. There's our input. We have some bias resistors over here. We'll talk about this much more when we talk about small signal amplifiers, but there is our basic configuration. And now this is a much more stable circuit. And so we can control the output based on the input much better. But important things to remember about the common emitter circuit is notice that when our voltage went up on our input, that the voltage went down on the collector. So we get a inversion. We call this a phase shift. Let's take a look at what I mean by that. Move these arrows out of the way, and let's put our signal back in there. There's our sine wave going up and down. Well, as the sine wave goes up, the output is going to go down. It should be bigger. As that sine wave goes down, the output is going to go up and also should be bigger. So there's a small signal coming in and a bigger signal coming out. But look, as this goes up, that goes down. As that goes down, this goes up. So we have a 180-degree phase shift. Recall from our AC circuits that if we have 2 signals that are opposite each other, one going up while the other goes down, they are 180 degrees out of phase. So we get a 180 degree phase shift in our common emitter circuit. And we'll talk more about that when we get to our small signal amplifiers. But let's see what we have if we turn this into a field effect transistor. That was a common emitter circuit. And remember, we knew it was a common emitter because the output was on the collector. But now we have a drain, a source, and a gate. So on the common emitter circuit, we knew it was a common emitter because the output was on the collector. Now the output is on the drain. So what kind of circuit is this? It's a common source circuit. So that is our second basic configuration. And once again, we'll see a lot more of that when we talk about small signal amplifiers. So let's look at the third configuration, and that of course is the common base. So let's draw our NPN transistor here. I'm going to put the emitter over there and the collector over here to our VCC. And our base is going to go to ground, and we're going to have some voltage that goes below ground for this to work. So we're going to have a power supply that's either two batteries. So there is our ground. And of course that means that those are connected together. So we're going to have some negative voltage and some positive voltage and a ground in the middle for this particular circuit to work, because we have the input on the emitter, and for this to work, this voltage has to go below the base voltage. So we have a positive voltage here, ground here, and we're going to have some negative voltage because this has to go less than 0 volts to get this to be 0 volts, and that has to be at least minus 0.7 volts for this to start turning on. So we have to have a negative voltage in the circuit for this to work. One way or another, we could have two batteries, or now let me redraw that battery. So here is our battery. Let's make that our ground. It's our positive, plus and negative. And we have some circuitry out here. And I'm just going to draw a little box here to represent our circuitry. But somewhere in there we are connected, and therefore this input voltage goes below ground. So we don't have to have it grounded, but we have to have some mechanism where the emitter voltage can go below the base voltage to get this to actually turn on. So we recognize the common base circuit mainly because the input is on the emitter, because we don't know exactly if this is going to be grounded or not, but it will be arranged in such a way that the base is a common connection between the input and the output. But the easiest way to recognize the common base circuit is the fact that the input is on the emitter. So common collector, the output is on the emitter. Common emitter, the output is on the collector. Common base, the input is on the emitter. Best way to recognize that. And of course, if this were an FET circuit, now we have the drain, the source, and the gate. So what we call that? A common gate circuit. And the input is on the source. So input is on the source, it's a common gate, and the gate is going to act as a common connection between the input and the output. So that is our basic circuit configurations, our common collector, common base, and common emitter. Or in the case of FETs, that's going to be common gate, common drain, or common source. And the next video we're going to get into small signal amplifiers, where we're going to elaborate a lot more on the common emitter circuit, which of course would be a common source circuit if it was an FET amplifier, but we'll concentrate on bipolar junction transistors. So I hope you found this useful and informative. If you did, please give me a thumbs up, hit the like button down below, and be sure to subscribe and hit the gray bell when you do to get notified when I put up new videos. And to take my free course in electronics technology and perhaps become a certified electronics technician or get a jump start in your studies as an electrical engineer, you can go to vocademy.net and sign up. It's 100% free. And a big thank you to my patrons at Patreon and my other donors. Without your support, I could not make these videos and I could not keep Vocademy free. So thanks again to my supporters and thanks to everyone for watching.